So I'm going to talk about series here. All right. So in this case, it's kind of a continuation of the sequence talk that we did. So if you need to pause at any point here, you are more than welcome to. If you need to write some stuff down, I'm going to kind of read through this because not all of this is very important, but it kind of gives you the background of what this is. So let's assume that you have that sequence of numbers we talked about in the previous section. All right. So if you take those same numbers, A1, A2, A3, etc., and you add them all together. So what if you take A1 through however many terms you have and add them all together? This is what we call an infinite series, when you add infinitely many numbers of a particular order together. So here's the kind of part I'm going to kind of run through really quick. The number a sub n is what we call the nth term of the series. We can think of it this way. If you just want to sum the first term, well, that's pretty easy. It's just A1. If you want to sum the first two terms, add A1 and A2. We are more interested in what happens when you sum all the terms together. That's kind of hard to do. Writing that out can get a little tedious, especially as you have more and more terms you're trying to deal with. So what you're going to see me use a lot in chapter 10 is this capital sigma notation. So for this example, we would think of it as the summation, the part on the bottom. This is where we start. We are going to start at a value, in this case, of 1. You see my first term over here was A1. The number on top is where you will end. In this case, we're going to end at the nth term. You notice that your last term is A sub n. This is your expression. This is very similar, if not exactly the same as the expression from sequences that we just talked about. So sometimes I will provide that to you. Sometimes you will have to find it on your own. So this is how you would note in a number of terms you want to add together. And what we're trying to build up to in this class is that I don't want you just to add n terms. I want you to be able to add infinitely many terms. So what about terms that go past the nth term? So what you will notice is that we're going to change our notation just a little bit. We're still going to do capital sigma. Now we're going to start still at 1. We're going to do n equals 1 as our starting point. Our ending point is now going to be infinity, because we're going to go all the way to the infinite term, and then we have our traditional expression on the inside. We are curious for the next few days of class is it possible to add up infinitely many numbers and essentially, for lack of a better analogy, can you get an answer? Is it possible to add up the answers and get all these numbers and get some answer? If that is possible, we call this a convergent series. Similar to the convergent sequence we talked about, it's a little bit more challenging to do convergent series, but that's going to be the goal. If you're not able to add up all these numbers to get a limit value, then we will say that the series will diverge, and that does happen from time to time. So that's what the rest of chapter 10 is going to be about. Sequences are great. They're very straightforward. Series do a lot more for us as y'all move into your disciplines. So here's some examples. Let's say you have something like, I want you to add all the positive whole numbers together. So what if you started adding up the numbers 1, 2, 3, 4, 5, 6, etc., etc.? Well, as you probably can guess, these numbers are being generated from an expression that we can just call n. If you were to plug all your numbers into n and add them together, you would get something like this. But as some of y'all can tell immediately, if you continue this pattern, eventually this is going to add up to infinity. If this adds up to infinity, then that's going to be a divergent series in this case. That means it's impossible to add up all your numbers to get a finite number. So this is something that we would think of as divergent. But a series that we're going to deal with in just a minute, and we'll talk a little bit differently, is what if something like this happens? What if you want to add up these particular fractions? Let's say you do 1/2 plus 1/4 plus 1/8 plus 1/16 plus etc., etc. As you might be able to tell, each of these numbers is coming from the expression 1 over 2 to the n. What happens this time, though, is that as you add these numbers together, unlike in the first example where every number is getting bigger and the series is getting bigger, in this case, each and every number is actually getting smaller and smaller. All right? That doesn't guarantee anything, as we'll see in just a little bit, but it's a good sign that if the numbers are getting smaller, then what happens is that sum is getting very close to a finite number. All right? If you're getting close to a finite number, our question is going to be, is it possible to find this finite number? In this particular example, which we're going to see in just a minute, this is called Zeno's paradox. All right, it's a popular series that some of y'all might see in other classes, but if you were to add all these fractions up and you kept going and going and going, eventually this would add up to exactly the number 1. Now that may not be very simple to see from here. Maybe it is for some of y'all who maybe are those kind of visual learners and kind of think abstractly like that, but my goal in this chapter is to show you kind of different mathematical methods to show this, or at least to verify that it's possible to do. So that's what we're going to kind of get into here in just a minute. So this leads me to the first kind of series that we want to talk about today. We're only going to do 2 of them because it's the first day of class and some people might add the class after lecture today. A very important example of infinite series is a series that we will call geometric. If there's going to be one series that some of y'all use in your other classes after this one, it's this one. Geometric shows up in a bunch of different classes of different disciplines, and I want to make sure that you are comfortable working with this. A geometric series has a very particular form. It has the form, if you were to write every term out, it would look something like this. You would have an a value plus an a times r plus an a times r squared plus an a times r cubed, etc. Your goal is, if the numbers are written out in this form, that doesn't really help us. We need to get it into the geometric series form that looks something like this squared box here. You need to write it as the summation from 1 to infinity. You need to identify your a value. The a value, as you can see, is the first number of your series, and then it's the common number in every term of your series. It's sometimes hard to see throughout the problem, so I always go to the first term and identify it from there. Then you have to identify your ratio or your R value, because that is the number that each and every term you are multiplying by that particular ratio. So it'll be a common ratio that you multiply by every time, and you will raise whatever that ratio is to the n minus 1. The reason you raise it to the n minus 1 is because you don't want the R value there on the first term. You want it there in every sequential term after that. So once you get the geometric series written out, this is what you're looking for. You really hope that if you take the absolute value of R, whatever this R value is, take the absolute value of it, if that number is less than 1, it converges. That is enough to show that a geometric series will converge. Now, one of the great things, and the reason why geometric series are so popular in other disciplines, is because geometric series, once you can show me that they converge, it's also very easy to find the sum of what these numbers will add up to. So the sum of a convergent geometric series will always add up to a over 1 minus r. So if you take the a value here and the r value here and plug them into this ratio, you can find the exact value of the convergent geometric series. Now, once again, this is only true if the absolute value of r is less than 1. Because as you can see on the very last line of this screen, if the absolute value of r is greater than or equal to 1, that means that your series actually will diverge. So let's look at some examples and see if we can work some of these together. So the first two examples say write the following as a geometric series that starts at n equals 1, and then determine if it converges or diverges. If it does converge, find its sum. So let's bring back Zeno's paradox. I showed you Zeno's paradox in its original form. We're going to put it into its geometric series form now. So for any geometric series, you're trying to write it as the summation from 1 to infinity of a times r to the n minus 1. So if that's the case here, this will be the summation from 1 to infinity. Remember, your a value is always just the first number, so that would be 1/2. Then you've got to find your r value that you're then going to raise to the n minus 1. All right? All you're doing for your r value is you're asking yourself, what number are you multiplying by to get to each successive number? So in this case, to get from 1/2 to 1/4, you multiply by 1/2. That same ratio, if you keep multiplying by it, will give you each number in Zeno's paradox. So this is your geometric series. Now, as far as the testing goes, this is your a, this is your r. They just happen to be the same number in this case. Geometric series say, first off, what is the absolute value of r? In this case, it's 1/2. That number is less than 1. So you have just answered your first question. This series converges by geometric series. That answers your first question. But now for the sum part of this, since it does converge and we did use geometric series, it has to add up to the ratio of a over 1 minus r. In this case, a and r are the exact same number. So if I plug those in, this would be 1/2 over 1 minus 1/2, which would end up being 1/2 over 1/2, which, as you can see, gives you a sum of 1. And if you go all the way back to when I showed y'all Zeno's paradox right here 2 slides earlier, you see I claim the answer to be 1. And going through the idea of geometric series, I have shown you that the answer is 1. All right, so let's do one that's not Zeno's paradox, so we don't actually know what the answer is. So in this case, we've got part B. 4/9 minus 8 over 27 plus 16 over 81 minus 32 over 243 plus 64 over 729. If we were to try to write this as a geometric series, this would be the summation from n equals 1 to infinity. Remember, a is just the first number. That would be 4/9. And then you've got to figure out what number are we multiplying by to get to each successive number. Well, let's see. Since the terms are alternating, you go from a negative to a positive to a negative. Well, I know you're going to be multiplying by some negative number, because every time you multiply by a negative, it changes the sign. It looks like you're multiplying by a 2 on top, because 4 times 2 is 8, and then 9 times 3 gives you 27. So I believe your ratio here is going to be negative 2/3. So there's your first answer. In this example, a is going to be 4/9 and r is going to be negative 2/3. So the absolute value of r in this case is going to be positive 2/3, which is still less than 1. So your series converges by geometric series. Same answer as you got above. The difference this time is that your sum is going to be a different number. So using the same formula that I used on part A, my a value is going to be 4/9 over 1 minus, and then here's the part that I think most students mess up on. Remember, it says r. You have to go back and pull the original r from the problem. In part A, r and absolute value of r were the same number. In part B, they're not. So don't use 2/3. Your original r value is negative 2/3. So you have to plug the negative value in for your sum formula. If we clean this up, this becomes 4/9 on top. On the bottom, that becomes 1 plus 2/3, which would be 5/3. And then we're back to our old keep change flip. 4/9 times 3/5. Let's see. 3 goes into 9 3 times. And if you simplify this, you should get a 4 on top and a 15 on the bottom. And so this particular series converges by geometric, and we figured out that eventually it would add up to the exact fraction of 4/15. Okay? This time, instead of me making you write your own geometric series, what if I give you a rendition of a geometric series and you have to do a little bit of manipulation on? For example, determine if the following geometric series are convergent or divergent. If they are convergent, find their sum. All right, on part A, it says the summation from 1 to infinity of 2 raised to the n plus 1 over 5 to the n. Now remember, geometric, your whole goal is you're trying to get it into the form of a times r to the n minus 1 power. In this case, I don't see any n minus 1s. I see an n plus 1 on top, and I see an n on the bottom. So what you're going to have to do first here is you're going to have to algebraically manipulate those two exponents into an n minus 1 power. For example, I eventually want this to be true. I want 2 and the 5 to still be there, but I want both of them to have a power of n minus 1. To do that, you have to ask yourself, if there are n plus 1 powers and you want it to be n minus 1, how many powers did you have to take away? Well, I know that n plus 1, if I were to subtract 2 from that, it would give me n minus 1, which means I need to break off 2 of the 2's. So we're going to break off a 2 squared into the front. Similar to the n on the bottom, if I want that n to become an n minus 1, all I've got to do is take one of them off. So I would factor off a 5 to the first. Cleaning this up, this would be the summation from 1 to infinity of 4 over 5 times 2/5 to the n minus 1. And you will notice that this now matches exactly your geometric series. In this example, your a value is now going to be 4/5 and your r value is going to be 2/5. Since the absolute value of r is still going to be 2/5 and that is less than 1 for the third time in a row, your series converges by geometric series. Then you can find the sum, because it does converge. Remember, that's a over 1 minus r. Your a value is going to be 4/5. Your r is going to be 1 minus 2/5. And let's do a little arithmetic. This would be a 4/5 on top. 1 minus 2/5 would be 3/5. And if you want to do your keep change flip again, this would be 4/5 times 5/3, where the 5's will cancel, and your final answer is 4/3. So a little bit more work that time. It's a little bit more of an abstract thinking idea, but that is a way you can manipulate a non-geometric series into a geometric series and do your problem. Part B is very similar. It says the summation from 1 to infinity of 5 to the 2n over 6 to the n minus 1. The good thing I see on this one is that I like the 6 to the n minus 1 because that already matches the power that I have in my geometric series foundation. The problem is this 2n? That doesn't look right because you can't just take away some like we did on part A and make it n minus 1. That too is a problem. So what you have to remember is from algebra, once again, I like the 6 to the n minus 1. That part's fine. In your exponent, from your exponent rules in algebra, if you have two things being multiplied together, like 2 times n, in exponential form, that would be the same thing as 5, and then raise that to both powers in order. So it would be 5 raised to the second raised to the n. We do it that way because now if we were to simplify this a little bit differently, instead of 5 to the 2n, I can write this as 25 to the n over 6 to the n minus 1. And while not exactly the same as part A, it's a lot more similar and easier to work with. So if you're looking to match this to a geometric series, you see the 25 and the 6. So eventually, you want this to be 25 over 6 to the n minus 1. Well, the 6 already matches exactly, which means I don't need to pull anything out, so I can leave the bottom as just being a 1. I have 25 to the n, and I need that to be 25 to the n minus 1. So similar to the 5 in the first problem, I need to take 125 out. So if you were to clean this up, this would be the summation from 1 to infinity of 25 times 25 over 6 to the n minus 1. This is technically your geometric series. Now in this example, A is 25, R is 25 over 6. So if you take the absolute value of R, that's going to be 25 over 6, which for the first time is greater than or equal to 1. That actually just means you can't do anything else, because by definition, your series now diverges by geometric series. And since the series does diverge by geometric, there is no sum you can find. Remember, a divergent series is going to end up going to infinity, so you don't need to worry about finding the sum here. So we're going to primarily focus on convergent stuff in Chapter 10, but occasionally I will sneak in some divergent stuff just so you're aware of what you're looking for and how to deal with it. All right, so nearing the end of today's lecture, one more thing I want to do with geometric series before we go on to the last little thing. You might remember from a grade school class that you probably learned that if you ever see a decimal with a bar above it, that means that that particular pattern repeats itself infinitely many times. For example, look at part A here. If you've got 0.23 with a bar over it, you'll probably remember that that just means that that 23 is going to keep repeating itself over and over and over. My question is, without a calculator, can you figure out what does this decimal, what would it be as a fraction? What fraction is 0.23 repeated? You can do that by setting it up as a geometric series. And let me show you that. How would we write this decimal as a geometric series? Well, let's think of it in parts. Think of it as, focus on the first 23. If you wanted to just write 0.23 as a decimal, you would tell me that that is 23 over 100. That is 0.23. Then you want to put another 23. So you would add to this, how would you get that 23? Well, it would be 23 over 10,000. All right. Then you keep going. Then it would be plus 23 over, so you want this one, it would be over, you need 6 zeros, so over 1,000,000. And so on and so forth. We do that because now if you look at this, you can now write this as a geometric series. This would be the summation from 1 to infinity. Remember, your A value is always the first number, so it's 23 over 100. And then what fraction are you multiplying by to get each of these terms? Well, it's just a 1 on top. And it looks like you're multiplying by 100 on the bottom, and you're going to raise that to the n minus 1. This is your A, this is your R. And once again, it's not asking you to determine convergence. I know it converges, we see the number, but you can kind of verify it if you'd like to. Since the absolute value of R, which is 1 over 100, is less than 1, we know it converges by geometric series. All right, so if that's the case, by geometric definition, we know that there has to be a sum that you can find as a fraction. So let's find that. A would be 23 over 100 over 1 minus R, which is 1 over 100. And this would be 23 over 100 divided by 99 over 100. And just to save a little bit of time on this video today, if you were to simplify this, it would come out to be the fraction 23 over 99. And so what you've just seen me do is by using a new technique like geometric series today, we can convert an infinitely long decimal into a fraction that can be written out. Now, it's not always two numbers they're going to repeat. Sometimes it's just one. For example, what if you want 0.7 repeated? How would you write 0.7 repeated as a fraction, or how does it come out to be what you may know it already to be? This time, it's just a bunch of sevens. So you want to write out a series of all these sevens being added together so that you can then write it as a geometric series. So if I did that, to get the first 7, that would just be 7/10. To get the next 7, that would be 7 over 100. And then 7 over 1,000. And plus so on and so forth. If that's the case, if we were to write our geometric series, your first number is your A, so that would be 7/10. And then the number that you're multiplying by to get each successive 7 here is this time just 1/10 that we're going to raise to the n minus 1. Similar to part A, you have your A and your R, and while we're not answering the convergent questions, we already know the answer to it, just kind of verifying here. Since the absolute value of R is 1/10 and that is less than 1, I know it's going to converge. That's our proof. But by definition, I can now find the sum of this series by using my convergent geometric series formula. So you would take your A value, which is 7/10, divided by 1 minus your R value, which is 1/10. And if you simplify this, you get 7/10 over 9/10, which simplified, just for time constraints here, you get a fraction of 7/9. Now this one, some people always tell me, oh, I knew that before you did it. And that's great. But now you're actually seeing why that is a true statement. This one you probably could do in your head maybe. The top one, maybe a little bit harder. You don't know what 0.23 repeated is in this case. But that's a way that you can use geometric and bring it back to something y'all probably haven't seen in a while, but you probably covered it in a grade school algebra class. All right, and then to wrap up this video, the last thing I want to cover for section 10.2 is an idea called the test for divergence. Before I get into the test for divergence, a couple of things to go over here. First off, the theorem at the top. If your series converges, so if we know that your infinite series is a convergent value, then A sub n has to approach 0 as n approaches infinity. And this comes from the idea of a limit that we talked about earlier. If you can take a limit as n approaches infinity and you get 0, that means that your series could converge. Now you got to be very careful about how you read this theorem. This theorem says if you know it converges, then the limit definition has to be true. But as you can see, I did red text for a reason so you don't fall for this trick. Theorem 7 does not say that the series converges if the limit goes to 0. it is possible for a series to diverge if your limit goes to 0. So think of it this way. If I tell you something converges, guaranteed fact, I know the limit goes to 0. But going the other way, or the converse of this, just because the limit goes to 0, that is not enough to answer the question. So while a limit going to 0 doesn't really tell you anything, here's where it can help us. It's called the test for divergence, which we're going to usually abbreviate TFD. It says the following. If a series diverges, all right, a series will diverge if the following two things happen. If the infinite limit fails to exist or is different from 0. So if you take the infinite limit and you get D and E, or you get anything other than 0, by the Theorem 7, that guarantees that it is going to diverge. Because by Theorem 7, if you know something converges, the limit has to go to 0. So the contrapositive of that says that if the limit doesn't go to 0, it's got to diverge. So we're going to kind of not use Theorem 7 exactly, but we're going to use what it tells us to be able to go backwards and change the idea to maybe answer a few questions. So now, while test for divergence is a very, very nice test, and it's really easy to use, it is sometimes misused when it's not supposed to be used. So what I want to do to wrap up this video is I'm going to show you an example of where test for divergence can be used, and then one where it does not need to be used, so you're not using it incorrectly. So last slide for today. Determine whether the following series are convergent or divergent. So it's just going to be, what's the answer, convergent or divergent? Part A says it's the summation from 1 to infinity of n times n plus 1 over n plus 2 times n plus 3. So based on our newfound rule, what it says is that if you take the limit of the expression you're given, so what you will notice is that some people can tell what this is right away. Some people might have to go a step further and expand this. So that would be n squared plus n over n squared plus 5n plus 6. Just kind of expanding and saving some time here. If you take the infinite limit of this ratio, since the power on top and bottom match, you need to use the ratio of coefficients to answer this. Your answer would be 1. Now, since this is a series, since this is not equal to 0, that means you know the answer. By your rule we just learned, your series diverges by TFD. In the previous section, this is where you got to be careful at. In the previous section, getting the answer 1 was okay because it was a sequence. Since this is a series, you need to make sure if it doesn't go to 0, that you immediately say that it diverges. That's where test for divergence is intended to be used. But here's an example where I see students misuse it, and I want to make sure you don't do it this way. On part B, the summation from 1 to infinity of cosine of pi n over 5 to the n. If you were to take the limit of this problem, you have a slight issue here in the fact that we can't evaluate the cosine of infinity. Because you probably remember that a cosine graph does something like this, where it keeps going up and down and up and down. So you never actually get an answer. So you can't actually do the infinite limit of this problem. But what I know is that a cosine graph from trig never goes higher than 1 and never goes lower than -1. And actually where this is going to be beneficial to us is that for every n value that you plug in here, you're either going to get a cosine of an odd pi value, so like cosine pi, cosine 3 pi, 5 pi, etc., or you're going to get cosine of an even pi, 2 pi, 4 pi, 6 pi. Either way, your answer is going to always be a positive or negative 1. So why is that beneficial to us? It's beneficial because instead of doing a limit problem, which is not going to help us here, I want to talk about rewriting this series. Now the 5 to the n, not much you can really do with that. We're going to leave it alone. But since cosine is just going to alternate, and that's the key word here, since it's just going to alternate between, let's see, if you plug in 1, cosine pi is negative 1. So between negative 1 and positive 1, back and forth, why don't we write that as an alternating term that we talked about 45 minutes ago? So you're just going to be alternating between negative 1 and positive 1. So I'm going to take negative 1, and I have to raise it to a particular power that the order does matter. So like I said, when you plug n equals 1 in, that first term is going to be cosine of pi. Well, cosine of pi is negative 1. So that means I need my first term to be negative. We talked about earlier, if you want your first term to be negative in a sequence, and the same thing applies to a series, you need your power to be n. So what we've just done is we've turned a trig series that we could not solve using tests for divergence, because we don't know how to evaluate this. We turned it into a different series that now reminds us of something we covered about 15 minutes ago. This now looks like a geometric series. So I can now rewrite this, because remember, your goal is to get everything as a power of n minus 1. So if I were to try to convert this into a negative 1/5 raised to the n minus 1, I would need to take 1 negative 1 off the top, and I would need to take 1/5 off the bottom. And as you can see, this actually matches exactly to your geometric series formula that we did earlier. And what we know is that this is your a, the negative 1/5, and r is negative 1/5. And if you take the absolute value of r, that would give you 1/5, which is less than 1, which by our definition says the series converges by geometric series. And so I use this last example and not try to be tricky. Someone always asks me and tells me, why are you trying to trick us on this particular section? It's not that I'm trying to trick you. It's that over the years of me teaching this course, I have so many students who try to misuse tests for divergence and don't use it correctly. Only use that rule if you can guarantee that your limit goes to something other than 0. If you run into something like we did here, and you don't know how to do that limit, try to find an alternate way to solve it like I did here. So that officially ends section 10.2. That actually also finishes the first homework material that is on MyLabs Math. So as a reminder, you need to get registered for MyLabs Math because the first homework is open. It's due Thursday night at midnight. Tomorrow, December 14th, we will be going back and doing live stream like I intended. Actually, during my video here, the internet's come back up on campus, so it should be all good to go tomorrow. So tomorrow we will meet in a live stream. I will be covering sections 10.3 and 10.4. Please make sure you have watched this video and understand the topics, because we will use some of these topics again tomorrow when I cover those two sections. If you have any questions, please feel free to email me. I'll be in front of my email most of the day. And have a great rest of your Tuesday.